Welcome friends and welcome back to the course. In this video, we are going to talk about primitive opposition. Let's get started. So here, in order to implement the different functionalities, the author decided to use ints to represent certain stuff. For example, there are calculation methods, and for each calculation method, he denotes an int to describe it. For example, this calculation method, if it contains the value 2, it means you are using ISNA. For example, if it is 4, we are using Mecca. If it is 7, we are using custom method, right? What's the problem with that? Like, at the end of the day, it is just a field containing some data. And the problem is that sometimes you can run into some issues, right? Some bugs that we don't understand why. And also we don't understand what is the bigger picture here. For example, I can make this field a value of 9, for example, 10 or 100 or any kind of number. And we won't get any type of feedback or help since here we are talking about statically typed language such as Kotlin, right? We want to use this in our favor, right? For example, by defining some types for these values, and then we can lean on the compiler whenever we make a mistake, for example. And if you notice, this is used a lot in this project. For example, for asterisk, for time format, latitude and longitude, of course, we don't have to change them. Like this thing are pretty fine. Adjust higher latitude methods, it's also a problem. And even in the return types of the function. Here, for example, this number of iteration is pretty fine because it describes a number of iteration. This is pretty fine. This is a value usage of an int, but sometimes you are using it the wrong way. Here, another example, we are going to talk about this in the next video, which is double array here. We are using a double array, which is kind of primitive opposition, of course, to return two different things, which is the declination of the sun and the equation type. Other stuff are pretty fine. For example, the compute midday, the compute time, for example, compute answer. These are valid things, even though we can wrap it into some kind of type that will help us in the describing of the domain problem much better. But at this time, you can change this primitive into something much better. We are going to start with some basic enums. And then whenever there are some logic regarding these types, we can start moving gradually this logic into either the enum, or maybe we can convert those enums into classes that will contain some function. Especially it will happen with this class. But let's start with this thing. Here I have created an enum to denote the time format. This is a simple thing, time 12 no suffix, time 24 and time floating. And then we can change the type of this format into a time format. So instead of 0, we are going to use, so 0 means 24. So we can use time 24 directly here. Of course, try to import it and then we can remove this thing. We don't need it anymore here. This is much better. Then what we can do, we can delete this 3 things. And now we do have some problems we need to fix. This is leaning on the compiler, of course. Here we are checking if time format is floating. So we can convert it directly to time format floating like the following. That's fine. Here, the beauty when using when with enums, we can have the following stuff. We can use add remaining branches. And then for 12, we know that this is the thing we to do. No ns, it means this one, right? And for everything else, it's just adding like the following. So we can push the else. Yeah, exactly. We don't need this too. We can do the else because we know if it is floating, we are going to deal with it here. So that's fine, I think. And now the problem is that we need to check if the tests are working, but we need also to fix the test because here in the test, we are using the primitive across all the functions. So we need to fix those. So here, I think it is only time 24. This one's time 24. This one also time 24. So these are pretty simple thing, pretty fine. I think there is also issues here. No, we don't have any issues here. We need also to create a converter to convert this int into a time format. You are going to create that also. So as you can see, we have added a time formatter. This is simply converting 1, 2, 3 normal primitive because that issue we created that pre-time cases with those primitive in mind. So we need to deal with them. So here are the time converter. We use time format and simply we use that time format. That's pretty fine. If you run all the tests are passing. That's pretty much it. And we need to do that for all of the cases, especially the calculation method, the asterisk, and also this adjust higher latitude methods. I think that's the most primitive problems. Now, as you can see, I already did it for this 2 stuff, which is high latitude types. I created that for just high latitude types. It is just 4 main things, as you can see, and also created this for asterisk. Now, for the asterisk, I also captured one interesting property, which is the shadow length. As we said previously in the first video of the domain problem, is that there are different school of thought when calculating the asser time. As we talked, people think that it is when the shadow length of any given object is twice the length of the original size. Other people think it's just the same length. So as you can see, we captured this thing and we used it here, right? If you check the shadow length, we used it here. Previously, it was like following, it was 1 plus the asynchronicity. Previously, it was 0 or 1. And then with this 1, it become the twice the length or the normal length. But here we extracted like the following and it's working pretty fine. The same thing happened here for this higher latitude types, right? We used it in this object and then we used it in different places. For example, in the when here, well, basically here in the calculation, we are doing nothing. We can extract and make this much better. Sometimes when you extract this kind of type, you discover that there is other refactoring you can do. So we can denote it like the following. You can create a calc like that directly. You can make it var here. And here we can give it the value of 0.5 because it is just assigning, right? And here, let me delete that like the following. And instead of doing the calculation here, I can remove it like that. Awesome. Now I can delete that. Exactly, we don't need a var, so we can convert it to a val, and directly we can return from here. And of course, we do have the test to check if everything is working fine. We also did the refactoring to the test because we needed that higher latitude converter because we were using the normal primitive obsession, of course. So I had to change this one with higher latitude. For the asynchronistic, I didn't create a custom converter. I just create the method that will create two types from different asynchronistic. If it is 0, we are using Shafi'i, otherwise you are using Hanafi. Sometimes you can use the other approach. Sometimes even for these converters, we could use this approach, but let it be. That's pretty much it for this primitive obsession. Say there are this calculation method problem, so I will leave this as an exercise and a practice. So try to do this thing and also this calculation method so that in the upcoming video, I'm going to talk about it since it involves some custom parameters which are this thing. These custom parameters are related to the calculation method, so we can create one simple class that will encapsulate everything. We're going to talk about it when extracting logic to classes. So this is pretty much for this video. So try to practice removing primitive obsession. That's it. Thank you very much and see you in the upcoming videos.